In Chapter 7, we're going to talk about work and energy. Both of those words get thrown around a lot in everyday life, but they mean really specific things. Physics usually defines energy as the ability to do work or the ability of an object to change itself or to change its environment. We know that energy has lots of forms. You've heard lots of forms: nuclear energy, solar energy, electrical, chemical, magnetic, potential, kinetic. We're going to be concentrating on mechanical forms of energy at this time. Mechanical energy comes in two basic forms. We usually abbreviate mechanical energy either ME, or sometimes you'll just see E for energy. There's two forms. One is kinetic. That is energy due to motion. If I throw a baseball and I hit a window, I can break the window. Obviously, the baseball has energy because it's capable of changing its environment. It can break a window. Okay. The other type is potential. We generally think of this as a sort of latent or stored energy. We're going to concern ourselves with two types of stored energy. One is gravitational potential energy. Gravitational potential energy is an energy that's due to an elevated position. If I have two bricks and one brick is 10 meters above the ground and I drop it, it can do a lot more damage than a brick that's only 1 meter above the ground and I drop it. When that brick falls from a much higher height, it's going to gain a lot more kinetic energy on the way down. Okay? That higher elevation gives that brick more energy. We call that gravitational potential energy. Usually I didn't write down how the symbol for kinetic energy is always going to be a K. Potential energy is a U. Not really sure why they picked a U, but that's our symbol. Gravitational potential energy will usually be a U with a little G next to it to show that it's gravitational. The other type of potential energy we're going to talk about is elastic potential energy. Now, elastic potential energy is energy that's stored by stretching, compressing, twisting, etc. So rather than being due to an elevated position, this is due to stretching, compressing, twisting, etc. It's some type of distorting of the shape. Think of springs, think of rubber bands you can stretch, think of basketballs that compress when they hit the ground. That's elastic potential energy. It's a distortion of the shape that causes the object to store energy. A lot of times really just temporarily. If a basketball hits the ground, it momentarily takes that kinetic energy, it compresses, it stores it as potential, and then when it springs back, the ball goes bouncing back up. So it doesn't lose all of its kinetic energy when it hits the ground. Mechanical energy, well, let me start off by just saying, before we go any farther, conservation of energy is one of our fundamental laws of physics. You cannot create energy and you cannot destroy energy. However, energy is converted from one form into another all of the time. We often convert mechanical energy into a form called heat. That's unfortunate because heat is not as useful. One of the problems with friction, that's exactly what friction does. Friction will convert mechanical energy into heat. You only have to see that because we've all done this. We rub our hands together, but just the friction of rubbing our hands together generates enough heat that our hands feel warmer. Okay? So, friction generates heat. Heat is not mechanical in nature. All right, so that's just kind of a general introduction into energy. Let's now just talk about work. We said a minute ago that energy is the ability to do work. Well, in physics, work has a very specific meaning. Work is equal to the force times the distance, or times the displacement, really is a better word, when force, that's a symbol for force, and displacement, and S is a common vector used for displacement. A lot of times I use delta X, are in the same direction. If you want to think about it, suppose that you have some object right here, and it's being moved this direction, so that's our displacement vector. But the force is actually in this direction. If we think about it, only the part of the force that's in the same direction as the displacement can actually be causing the work, can actually be moving the object to the right. The part of the force that's lifting up doesn't cause it to move, but the part of the force that's horizontal is causing it to move. So in this case, the way I've drawn it, only the X component is doing work. A lot of times we see our formula for work written like this. It's the component of the force that's parallel to the displacement. The two little lines there mean parallel. Or we might prefer to write it that it's F. The parallel component here would be cosine theta times S. Although we usually see it written more like this. And a lot of books will even use D for distance. So this book uses S, so I'm using S. I like this one the best. Actually, I kind of like it better with a D, but what you want to remember is theta is the angle between S and F. Okay. Now, notice thing you might notice about this equation is we actually have two vector quantities, but this only is the magnitude of the vector. This is not actually a vector equation. Work is scalar. What's that mean? It means work is not a vector. It does not have a direction. The unit for work is the same as the unit for energy. It's the joule. The symbol for a joule is a capital J. Unlike some scalar quantities are always positive. In particular, speed and distance are always positive quantities. However, other scalar quantities like temperature, they can be negative. Work can be positive or negative, and we'll come back and we'll talk more about that. But basically, work is positive when the force is in the direction of the displacement. So, let's just say you're pushing something horizontally to the right, and the object's moving horizontally to the right, then you're doing positive work. However, friction would be pointing to the left. So although you're doing positive work on the object, friction would actually be doing negative work. Anytime you have a force that's in the opposite direction as the displacement, that force will be doing negative work. Okay? So work can be positive, work can be negative. We can also have zero work. The y component of this force, if we looked at just the upward part, is doing absolutely no work. If I have an object, let's look at this marker in my hand just because it's an easy object. If I push up on it, I'm doing positive work because I'm pushing up and I'm moving it up. But if I slide this marker horizontally, I didn't finish my other thought. If I push up on this, I'm doing positive work. The gravitational force is pushing down. So when I'm doing positive work, gravity is actually doing negative work because the gravitational force is down, but the displacement's up. Now, if I move it sideways, gravity is doing no work, right? Because the gravitational force points straight down, but the object's moving horizontally, so the gravitational force does not have any part of it in the direction of the displacement. So in order for a force to do work, two things have to happen. One, the object has to move. If I go push on this wall as hard as I can, I'm pushing and grit my teeth, strain. If the wall doesn't move, then I did not do any work on the object. So if the displacement is zero, clearly no work is done. The other thing that has to be true is at least a component of the applied force, or the force you're talking about, has to be parallel to the displacement. Parallel. It could be in the same direction. You could be pushing to the right and it might be moving to the right. Or it could be in the opposite direction. You might be pushing it to the right, it might be moving it to the right, but there could be a frictional force to the left. That frictional force would be doing negative work. So when they're in the same direction, positive work is done. When force and displacement are in opposite directions, negative work is done. If the force is perpendicular to the displacement, that force does no work at all. Let's look at a couple of examples. Steve uses a 210 Newton force to push a car 210 Newtons. I'm sorry, looked at the wrong number. 19 meters. How much work is done? Well, first of all, it depends on the direction of the force. So for part A, we're going to assume that he is pushing horizontally in the direction of the motion. So if the force is this direction, 210 newtons at 0 degrees, then the work done would be force. We can write the formula. I'm going to write it with D, force, distance, cosine, theta. Like I say, some books will use S, some will use a theta, some will use a phi. It's okay. You just need to know that if the force is this way and the displacement is this way, the angle between them is 0. Cosine of 0 is 1. So it's always easiest when they're the same direction because cosine 0 is 1. So we get 210 newtons for 19 meters. Cosine 0 is 1. I just multiply that. And it comes out to about 4,000 with two significant digits of 4.0 times 10 to the third joules. A Newton meter is a joule. Look at a Newton is a kilogram meter per second squared. So really this is a kilogram meter squared per second squared. But just know that we get the simplest way to write the unit for energies in joules. All right, what if instead he's pushing, but he's pushing it at an angle, maybe he's taller than the car, so he's kind of bending down and pushing. So he's actually going to push at an angle of 210 newtons still, but he's pushing at an angle of 30 degrees below horizontal. Our displacement vector is still 19 meters at 0 degrees. All we need to know, it doesn't even matter whether it's above horizontal or below horizontal, what is the angle between the displacement and the force? Well, the angle is going to be 30 degrees. So I do the same thing. He's applying 210 newtons for a distance of 19 meters, but this time we have cosine 30 degrees, and he does about 3.5 times 10 to the third joules. He obviously did less because not all of the force was in the direction of the motion. I want to add something to that. What if I told you that there was a frictional force, and the frictional force was 5 newtons? We know that if we had a frictional force, let's put a part C over here. The frictional force would oppose the motion. So if the displacement was this way, the frictional force is the opposite way. So let's suppose the frictional force is 5 newtons. We'll keep two significant digits. So it's going to be 5.0 newtons. Anytime, look at this. This would be work equals force times distance times the cosine of theta. So we have a 5 Newton force, 19 meters, cosine of 180 degrees. When vectors point in the opposite direction, the angle between those vectors is 180 degrees. We know that cosine 180 degrees is -1. And so really it just comes out to be whatever the negative of 5 times 19 is, or negative 95 joules. So if he's pushing at 210 newtons at a cosine 30 degrees, he's doing this much positive work. But friction was doing this much, yeah, I got it right, this much negative work. Now, truthfully, that friction force is probably way too small. Let's make it a little bigger. If he's having to push with 210 newtons, he's probably got a frictional force, maybe more like 150 newtons. So if we make our frictional force 150, let's just change our numbers a little bit. Now I better get my calculator and be really careful. If I do 150 times 19 to two significant digits, that's going to come out to be about a negative 2.9 times 10 to the third newtons. So his push is doing positive work, friction is doing negative work. A lot of times with work, what we're interested in is the total work. So what's the total work? We'll just keep adding to this problem. That's also called the net work, as in total. That's a little tricky because we want to put those together and say a network, but it's not a network, it's the network. So work net. Well, a minute ago we came up with, and I don't want to use any rounded, so let's see what we had. We had 210 times 19 times cosine 30, and that was about 3455 positive work, and friction did negative, that's positive work, a negative 2,850 newtons. So the total amount of work, if you added up the work by all of the forces, 3455 minus 2850, came out to be about 605 joules of work, or to two significant digits, 610 joules. So that would be the net work. That's the sum of the positive and negative work done. Now, I did leave off a couple of forces. I didn't talk about the work done by gravity, and I didn't talk about the work done by the normal force. However, both of those are zero, because both of those are going to be perpendicular to the motion. So they make no contribution at all to the total work done. Any force that's perpendicular to the displacement, that's zero work, they make no contribution. Okay, let's do another work problem. Let's think about a satellite that's in orbit. So here's the Earth, and here's a satellite. It's in circular orbit around the Earth. Well, that's not a very good circle, but let's pretend that it is. The question wants to know, is Earth's gravity doing positive work, negative work? Half the time it's doing positive work, half the time it's doing negative work. It's a multiple choice, or no work at all. What kind of work is Earth's gravity doing? Well, it may or may not surprise you, but if you stop and think about it, the force is to the center. It's a centripetal force. When the object's right here, the velocity, the instantaneous velocity will be in that direction, which means that minute amount of displacement will be in that direction. That's perpendicular, so there's no work done. I can pick another point and go, well, but the force is towards the center, but but the displacement at that location, remember, instantaneous displacement and velocity always point in the same direction. The instantaneous velocity always points in the direction of displacement. So still perpendicular. So what we find is when something's in orbit, the gravitational force is doing no work if it's moving in a perfect circle. Now, if it was moving elliptically, it might do some work, and that actually happens with elliptical orbits. Elliptical orbits, the gravity does do work. At times it causes the speed to slow up, and at times it causes the speed to slow down. But in a perfectly circular orbit, where the speed is a constant, the gravitational force does no work at all. You can think about it, if we think a little bit about an elliptical one, just because I'm talking about it. In an elliptical orbit, let's draw one that's kind of obviously elliptical. It's really obvious that when the object's way out here, it's going to accelerate this way. Let's suppose it's going in this direction. It's going to be gaining speed as it gets faster and faster. But when it goes out here, it actually loses speed as it gets farther away. So it's gaining speed and losing speed. The gravitational force is actually changing. So under those circumstances, gravity is doing some work. It is exerting a force that has a component of the force in the direction of motion, but not for something moving in a circle. If the force is to the center of a circle, the displacement is tangent to the circle, or the instantaneous velocity is tangent, no work is going to be done. Let's do another really important idea. We've talked about total network. Let's look at an example. Of work done sliding down a frictionless ramp. So there's theta. This ramp has a height of h, and we're going to let this displacement distance here, from here to here, we'll call that S. We're going to start with a mass that's right up here at the very top, and we're going to move that mass till it's moved all the way down to the very bottom. So here the front edge of the box is at this height, the front edge of the box is at that height. And let's think about it. We know that the force that causes it to move down the ramp is the parallel component of its weight, right? We know the work is F parallel times S. Well, when you have the ramp, if you think of it, when it's sitting on this ramp, the force that causes it to accelerate is the parallel component of the weight. So F parallel is mg sine theta. Remember, when we have a mass on a ramp, we've already done this before. The parallel component of the weight is mg sine theta. The perpendicular or y component of the weight is mg cosine theta. It's one of the very few times where we don't say, oh, horizontal is cosine. Nope, in this case, horizontal to the ramp or parallel to the ramp is sine. So this is mg sine theta times S. Now, let's see what else we know with a little thinking. If we look at our trig knowledge, I know this is a right triangle. Look at that angle. That sine theta is always opposite over hypotenuse. In this case, sine theta is h over s. So the work done sliding down the ramp is mg h over s times s, or mgh. What if all we did was pick the thing, drop the thing? What if instead of sliding it down a ramp, I just dropped it and it fell a distance h? Well, think about it. The force in that case would be gravity if it's dropped. The gravitational force would be mg. The distance it falls would be h. And the amount of work done would be mgh. Oh, exactly the same. What it comes down to is if the ramp has no friction, the amount of work doesn't even depend on what angle. It could be dropped straight down. It could be at a really, really steep angle, really, really flat angle. But the amount of work that gravity does not depend on the angle. Okay, we've already talked about total work, so what I want to do now is move on to section 7.3, kinetic energy. Our definition for kinetic energy is simply that the kinetic energy K is 1/2 mv squared. That's our energy due to motion. It's obvious when we look at the formula that velocity or speed, really you can think of it as speed, that the speed, because with squared it's going to be positive, plays a much larger role than the mass. Another interesting thing is if you look at this, kinetic energy cannot be negative. Now energy can be negative and work can be negative, but kinetic energy is always going to be positive because there's no such thing as a negative mass. If we're squaring the velocity or the speed, that has to be a positive quantity. So kinetic energy is always going to be a positive quantity. Now, the change in kinetic energy could be positive or negative. You could increase your kinetic energy, or you can decrease your kinetic energy all the way down to 0. But kinetic energy is a positive quantity. I don't want to practice calculating kinetic energy because I know that you're capable of, I say the mass is 5 kilograms and the speed is 2 meters per second. You can go, oh, 5 kilograms, 2 meters per second squared is 4, 5 times 4 is 20, half of 20, that's 10 joules. I want to move on to something that's really important, and that's called the work energy theorem. And the work energy theorem says the total work, you might want to use the net work, same thing. The total work is equal to the change in kinetic energy. Or you could say, you could write it this way. Final minus initial. That's all the work energy theorem says, is that the total work done on an object, whatever that total is, determines the change in kinetic energy. So let's look at an example where maybe we have several forces acting. Let's see if we can find the total work. And let's find the change in kinetic energy. This example, I believe it's 7.5 in your book, if it hasn't changed, says that we have a tractor pulling a sled full of firewood. So here's a sled full of firewood, loaded up with firewood. And it's being pulled. Here's my tractor, big wheel here, little wheel here. And that's sort of what a tractor looks like. This rope makes an angle phi. The book uses phi a lot. I tend to use theta all the time. Here's the ground, nice and level. Let's make that touch the ground. There we go. Firewood full of sled full of firewood pulled by a tractor. And they tell us the sled weighs, now be careful, that's a lowercase w, 14,700 newtons. They tell me that this angle is 36.9 degrees, that the tractor pull is 5,000 newtons, friction is 3,500 newtons, and the displacement is 20.0 meters. There are two other forces we could talk about if we wanted to draw a free body diagram here, and we could. We've got a situation like this. We have a tractor that's pulling with 5,000 newtons. We have a frictional force that's opposing with 3,500 newtons. We also have a gravitational weight, 14,700 newtons, and a normal force. I don't even know for sure how big that normal force is, but I could figure it out without too much trouble. Now, there's lots of ways we can do this problem. We could stop and we can find the total force first. What's the net force? Or we can find the work done by each force separately and then get the net work. I'm kind of inclined in this case, I'm really only concerned about the forces that are doing work. And the forces that are doing work are friction and the horizontal component of the tractor pull. So I know gravity's doing no work because it points down. I know the normal force is doing no work. Okay. I know that the y component of this tractor pull, the upward and the normal force combined equal 14,007. I don't care. I could stop and figure out the normal force if I wanted to. I could stop and figure out the coefficient of friction when we get done. There's a lot I can do, but let's just concentrate right now on using the work energy theorem. Okay, so what's the total work? Well, we have the tractor, and the work it's going to do is 5,000 newtons times 20 meters times cosine 36.9 degrees. When I put that in my calculator, I find out that it does 79,968 joules. Now, if I'm reporting this answer, let's rewrite this as 5.0 times 10 to the third. We'll write it so we have at least a couple significant digits. Let's write it, but we have 3. I'm good. Let's see. We'll write everything with 3 since they gave me the angle with 3. Okay. let's assume that they gave me 3 significant digits on everything. So the work done by the tractor, that's not to 3 significant digits, but I certainly could rewrite it there, and I also miscopied. No, I didn't. That would be about 80.0 kilojoules. So if my final answer was just how much work did the tractor do, that would be my answer. And the work done by friction, friction is about 3,500 times 20. Cosine 180 degrees, that's that -1. Friction is at 180 degrees. It's in the opposite direction of the displacement. And that comes out to be, I don't know, that comes out to be 70,000 exactly. Or 70.0 kilojoules. So, what's the total? What's the net work? Well, it's going to be 79,968 minus, oh, and I didn't write that negative, but it's very definitely negative, minus 70,000. So our net work, or our total work, is 9968. Again, if we have 3 significant digits, that's about 10,000 kilojoules. That's going to round up to 10,000, or 1.0 if you want to write it. We could write it not in kilojoules, but there's our total work. Okay, let's go with that 10,000. Let's answer a second question about this. If the initial speed of the sled was 2.00, you want to do 2 or 3 significant digits, meters per second, we'll keep 3. So if that, how fast, or what is the speed? Find the speed after it's moved 20.0 meters. In other words, after all this work was done on it. Well, that's where we're going to use the work energy theorem. The total work equals the change in kinetic energy, or K final minus K initial. So our total work done, let's not round, was 9968 joules. Our final kinetic energy will be 1/2 mv final squared, and our initial kinetic energy will be 1/2 mv initial squared. Okay, they didn't tell me the mass. All I have to do is take 14,700, divide by 9.8. It has a mass of 1,500 kilograms. So I put that in, so I've got 9968 equals 1/2, 1,500 kilograms. V final is what I'm looking for. I don't know the final speed. Minus 1/2, 1,500 times 2 squared. Let's think about this. to be 750 times 4. That's 3,000. Add 3,000 to both sides. I get 12,968 equals 750 V final squared. Guys, we're down to just punching calculator buttons. 12,968 divided by 750. Take the square root. And I get that the speed, well, I can write this two ways. The speed is going to be 4.16 meters per second. Actually, that's going to be the velocity also, because we know the velocity is in the direction of the displacement. Okay. When you take the square root, you get a plus or minus situation, but in this case, we know the speed cannot be negative. So, there you are. If it started going, if it was 2 meters per second initially, then at the end it has to be this. A lot of times on these problems, the object starts off at rest. If the object starts off at rest, then the initial kinetic energy is 0. If the initial kinetic energy is 0, then the total work done has to equal the final kinetic energy. But in our example, it already had some kinetic energy before it even started. So when we did work, it simply just gave it even more. So if it started, it had 3,000 joules of kinetic energy. After we did our work on it, it had 12,968 because we added that additional 9,968. Okay, that concludes the first lecture over work and the work energy theorem.